Noon. Hi, everybody. How's everybody doing? Doing okay? Very good. I'm going to be reading off of some notes occasionally on my laptop because I'm an academic. I didn't used to be, but I guess 10 years in academia has made me that. And so I've got notes. And this is part of some research work that I've been doing that's actually based on practice. So I'm a professor of practice, which means I do things, and then I write about those things, and then hopefully they're good. Sometimes they are. Most of the time, you know, middling success. So I will tell you, if this seems like you're in a college classroom again, I apologize. I teach in college classrooms. This talk is basically a question, and that question is, why do we choose specific hardware in our designs, and how might we choose hardware components with purpose by considering their affordances? And that's not the last time you're going to hear that word. And it's important to note at the head of this presentation that this is all early work, and I by no means claim to have many answers, only more questions that we can hopefully explore further. And I've given a rougher version of this presentation in the past to my students who have to pretend that they like it. I'm excited to be here where I can actually get meaningful feedback after this on how we might be able to move forward. So my name is Jayson Margalus. I am first and foremost a design. I work in industrial and game design. I taught for 10 years at DePaul University. I started out as a game design professor there, and then I created an industrial design program. And I am currently at a university called Washington and Lee in Lexington, Virginia, about 2.5 hours outside of Washington, D.C., where I am the Johnson Professor of Entrepreneurship and Leadership and the Director of the Connolly Center for Entrepreneurship, which is a very long title that just means I run entrepreneurship there. So who am I as an educator? Because none of you know who I am, I'm sure. I teach game design. I love this image here, actually. This is my students presenting a pinball machine that they designed to George Gomez, who is the Chief Creative Officer of Stern Pinball. Over there is Eugene Jarvis, who created Cruisin' USA, Defender, and a whole bunch of other games you've probably heard of. He runs Raw Thrills. And then the guy who is actually taking that picture is Josh Sway, who ran the company Robomoto that made all the Tony Hawk games. So I teach my students how to make games. I also make makerspaces in academic context as well as nonprofits. At DePaul, I created the Idea Realization Labs 1 and 2. At Washington and Lee, I'm working on a new space called the Connolly Center. And I teach industrial design, so I teach people how to make objects and well-designed objects, I hope. As a practicing professional, I did for a number of years run a video game company. We have games on Steam, browser-based games. We also have a game that we worked on with medical professionals for therapy. I make game hardware. So for the last 7 years, I've made the badges with a couple friends of mine for a hacker conference in Chicago, which we'll talk about in a bit. And then I make medical stuff. So during the pandemic, I actually raised about 150 grand to build and design flat pack face shield with a friend of mine whose name is Jeff Solon. We distributed them all throughout the Midwest. Make Magazine wrote about that a little bit. And then I made recently a microscope that is actually deployed in field hospitals right now in Africa, and it's for head and neck cancer and dramatically reduces the cost of care. So anyways, who's this talk for? It's for anyone who makes hardware and would like to know a little bit about how a designer who's not an electrical engineer, I kind of like muddle my way through KiCad and I muddle my way through Eagle and stuff like that to get to the end products. But how a designer might think about making hardware and how you could leverage that thinking to make usable, consumer grade, and maybe pleasing to use things sometimes. And this talk is about, the second time you're going to hear affordances now. It talks about affordances, which is a word we use in design. How many people have heard of affordances, this term? Everybody? Some, okay. How many of you are familiar, who raise your hand, with Janet Murray's work in affordances in computing? Okay, so this will be somewhat new. This is good, okay. And how we apply them to hardware design. So I'm going to read my notes here again. This talk explores the concept of affordances in the context of hardware components used in game consoles and interactive systems. Drawing on the theories of James Gibson, Don Norman, Janet Murray, and contemporary thinkers like Bogost, Harman, Baudrillard will examine how hardware affordances shape user interaction, engagement, and design innovation by synthesizing insights from design theory, phenomenology, and media studies. I'm hoping to provide a comprehensive framework for understanding and leveraging hardware affordances in the development of immersive and intuitive interactive systems. It's a lot of words, right? It's a big word salad. So what? It's very important to me, at least, to create objects that speak, things that are not only usable but pleasing to use, and things that show us qualities about the world or others or ourselves that we may not have seen before. Basically, as Dieter Rams calls it, honest things, creating objects that are honest. So I'm going to start off by using an example of a thing I made or co-made, that the struggles of developing it, and ultimately how I came to understand how to design for hardware better. So this is a badge I made for, and I'm going to have to digress here real quick. For a conference that's its name, the first 4 letters of the name are in the Urban Dictionary and mean something else, and I only say this because the conference started before that word, which is not a good word, began, and it stands for 312, which is the Chicago area code. So when I say ThoughtCon, it's not a bad, it's a great conference, but the people who started refused to change the name because they say our name was here for half a decade before, that word came about. So with that explained, and I have to explain that because every time I give this lecture to my students, they laugh at me. And so I just need to give you that up front. This is one of the first badges that I ever got to work on. And because I came in after the hardware had already been developed, I had a challenge, which is how can I make a game experience on a device or have no control over its design? And so I do what designers typically do. You get out your notebook, start sketching ideas, you put them in front of people, and you're basically doing early, low-fidelity stage prototypes. You're asking people, what do you think about this? And I did this for a couple months for the ThoughtCon OX8 badge, which was in 2016, and I got nowhere. I got absolutely nowhere. And so I took some time off, and I started thinking, like, what are the parts of this thing? What are their purposes? And what are the complexities? How do those parts interact with each other? And this is something called affordance mining. Right around that time, I was also playing like a lot of chess for some reason. I don't know if a lot of you do this, but like when you're stuck on a problem, you start groping around into other unknown areas, and then you find out that your brain's actually doing it on purpose, and it's like you didn't know it the whole time. So I was playing a lot of chess for some reason, playing a lot of like old roguelikes. Any roguelike fans here? And does anybody know what this is? Meggy Jr. RGB is by Evil Mad Scientist, actually. So I was playing a lot of this, and it's an LED matrix with RGB LEDs in it. And I'm thinking to myself while I'm doing this, like, okay, well, I've got some of these components. I've got some LEDs in this device. I've got some potentiometers with some letters and numbers around them. And I've got an ATmega 32U4 chip, which can save and rewrite data. And importantly, I can also plug a computer into it and talk back and forth with the computer using the device. So thinking of these affordances, I revisited the badge and came to notice some things. For instance, the LEDs were positioned in such a way that they can indicate directionality. So the top LED would be north. This one over there is to the left, right, or to your west. The next one to your east, and the other one to your south. These are RGB LEDs too, so I can indicate that there are different kinds of things in those directions in front and behind me, right? I also started to notice that I got these potentiometers, which are really interesting because they look like the directions on a chessboard, right? Like knight moves to, I don't know, K6 or however that, right? And so like my brain had kind of tricked me into thinking about this device and what else it could do, how it was speaking to people in ways that I hadn't noticed before, based on like all of the things that are in it. Okay, and what that ended up kind of looking like was something like this. So these are little maps with, you see, letters and numbers. And we started to develop like these little rogue-like puzzles where people could navigate around the puzzles using the potentiometers and see what's in front, to the left, to the right, and behind them, okay? But then I've got this third potentiometer. And so what do I do with that? And I start thinking, okay, well, third could, convey like a z-axis, right? So you can move through these rogue-like puzzles as well. And so I'm listening to the device and listening to what it wants to be rather than trying to impose my idea of what it should be on it. And the point here, and the end result of this whole exercise, was that the design of a game that used the hardware intuitively, because it was designed in such a way as to listen to what the hardware wanted to be. This is the essence of something called affordance mining, based on work in symbols, semiotics, and design. Any Baudrillard fans here? No Baudrillard fans, that's okay. This next image is Mr. Rogers, who's actually counting to 2. Many of you have probably seen this. Middle finger was not what he was doing, right? So the study of semiotics and symbols is the study of how meaning is encoded into signs. Baudrillard said the sign has 2 parts, the signifier and the perception. Signifier is the expression that is made by a person or another object, and the perception is what the expression represents. So for instance, the meaning of a signifier, like ya, means I in Russian, but yes in German. If I do this in this room right now, it means you're doing a good job. What does it mean if I'm on the side of the road? I want a car, right? So this is what I'm doing. This is the signifier, and then your perception based on the context interprets that symbol in a different way. So the concept of affordances, I love this. Watch. Okay, so this is called a Norman door. You see how I tried to pull because there's a handle there and it was a push door? How many of you have had this experience? Very frustrating, right? The concept of affordances is an elaborate. Oh, funny thing. That was a door at a design university in Barcelona. So even design institutions have not gotten doors correct. That's right. So the concept of affordances is an elaboration on the idea of semiotics. It was first introduced by James Gibson in 1979 and refers to the perceived and actual properties of an object that determine how it can be used. I'm going to stop talking in a second. We're going to do a fun call and answer, but we'll get there in a moment. Don Norman popularized the idea of affordances in the design of everyday things in the context of human-computer interaction, emphasizing how design elements communicate their functionality to users. So he broke this up into two buckets. You have actual affordances. These are the real actions that an object can support. So a door handle can be pulled or pushed depending on its design. And then perceived affordances. These are the actions users believe they can take with an object based on its appearance. So like a button on a website that's shaded, looks raised, and then you think that you can press it, right? This is hopefully starting to resemble semiotics concepts of signifier and perception, by the way. So affordances are part of a larger map of language that we use as designers that also includes signifiers, mapping, feedback, and so on. Almost to the call and answer. So a signifier, this is important, so you have to remember this stuff because we're going to do a thing where you have to call it back out. A signifier tells us where the action should take place, like a door handle positioned a little bit above waist level. Mapping is the feedback that you get when you interact with the object of action. And conceptual models, these are very interesting. They're often cultural or context dependent, kind of like the thumbs up that I was doing before, but also sometimes innate. They use symbols that we already understand to explain complex new concepts. Thinking of like the pinch on the phone. This is something that feels intuitive. It's not something that always existed, right? We understand what it means, but it doesn't actually mean anything when we do it on a phone. It's just, it's arbitrary. All right, here's the call and answer. So let's use this new language to try and figure out what things are and how we should use them. We're going to do a little call and answer. I'm going to present you with some images, and you're going to tell me what you're looking at and how to use it. This is the first one's a gimme. What is this, and how do you use it? It's a spoon. What do we do with it? Yeah, we bend your mind. We shovel with the spoon, right? Homer Simpson, what does he say? What's the thing that I shovel the food with? Okay. I'm going to do a quick detour because I think spoons are rubbish. If you've ever watched a child try to use a spoon, they get things everywhere, when in fact they could just lift the bowl to their lips and drink the liquid that way. So this is what Tim Ingold calls where objects introduce problems, not solutions. Okay, getting back on track. What's happening here? That's that's right. They create yes, that's right. We've got a handle here. Handle denotes pull, and the pad, the plate, denotes push. So what's the problem? What's the problem with this? Why is this a problem? Makes no sense. You have to push on it because the object is really telling us to pull it. So you have to do more work. Okay, how about this? What's the problem here? Anybody know? Right. These are push pads, right? Everything in my brain knows that this is a push pad. And so somebody had to write pull on it to tell me to use it differently. These kinds of poorly designed objects are everywhere. They're everywhere. Okay, so that was a little bit about, a little bit about affordances. I want to talk about mapping really quick, okay? Left image right here. Again, this makes no sense. It doesn't fit a map. It doesn't fit how I understand the world. What is the left knob? Where does that correspond to in the burners? What about the one on the far right? Okay, now let's take a look at the image on the right. That's good mapping. The bottom left knob is associated with the bottom left burner and so on, okay? So mapping is important when we think of design, just as affordances are, because it's the way that our mental models of how things ought to work are conveyed to us by designers. This is good mapping. That's a chair and or a seat in a car, and it looks like a seat in a car. And so when I move the things that correspond to the seat in the car, they're going to do things on that seat. All right, another call and answer. What's that? I have no idea. I like the seat. M means maybe, and it's like an eject button or something. Let's take a look at this. Okay, so you got the door lock on the left-hand side, and you've got the control that controls the door lock. What's the problem here? It should be flipped, right? Because up means unlock and down means lock. So the mapping is incorrect here. Oh, this is my favorite one. These are things that actually exist in the world, okay? So we got some problems here. We've got the two up top. I actually work at a university where one of our buildings, the main floor that you walk into is 1, and then as you go down, you go to 2, 3, 4, 5. So this is not new. And then the one on the left, I mean, well, I really have no idea what's going on there. Okay, this is good mapping. How many of you are familiar with Shigeru Miyamoto? One of my favorite designers, excellent game designer. He introduces the language of games in a way that was, at the time, incredibly groundbreaking. Okay, so you've got an old NES controller over here with the D-pad, select and start buttons, and then the A and B buttons. And Miyamoto opens the game to Mario with a Goomba that's walking slowly towards you. And you've got this controller, which is like your way to interface with the world. So what do? You start pressing buttons, right? And very quickly you learn that you got to jump, because if you don't jump, the Goomba's going to get you, and you might die a couple times and then figure it out. So he's teaching you the language of the controller, and it's unfolding as you're playing the game. As you further move through the level, you get like a little glowy box. You jump and you hit the glowy box, and a mushroom comes out, and then you get bigger. Then you have to jump over chasms, right? So now you're doing an elaboration of the language that he's teaching you. So the affordances of the controller, the buttons itself, are being taught through the software. It's brilliant if you've not played this game. Brilliant, brilliant game. Okay, we're getting close to how this connects to hardware, but you might be seeing some of it already. So Janet Murray extended Gibson and Norman's idea of affordances to digital environments in a great book called Inventing the Medium. She's from Georgia Tech. She identified 4 key affordances for the computing medium, and they are spatial, procedural, participatory, and encyclopedic. This is basically how a computer talks to us and tells us to use it. It's these 4 key affordances. Okay, so we're going to dive into these 4 concepts and then get to the meat of the talk, where we explore these affordances in the realm of hardware components, particularly ones used in game consoles, controllers, and then we'll offer a brief analysis of how they might shape experience and interaction. Okay. So the 4 key concept. This is one of the games I made that's on Steam. It's called Delve Deeper. Or co-made, sorry. So the 4 concepts. The first one is spatial. This affordance involves the creation of navigable, often 3-dimensional spaces within digital environments, allowing users to explore and interact with spatial representations. Virtual reality environments is an obvious one. Video games, digital maps, operating systems is a huge one. When the operating system was created, there was a thing called a desktop, which is not an actual desktop. I don't know if we need to talk about that very much, but it's not a real, you don't put papers and pens on it. But it makes sense to us. This is the desktop. This is where my documents go. This is where my files go. Okay? So that's a spatial way to navigate a computer that didn't exist before the operating system. This game was made by the way, by my game company Lunar Giant, which is an anagram for Alan Turing, and it's based on Carcassonne. Any Carcassonne fans in here? Couple. Okay. Second one is affordance is the procedural affordance. This affordance emphasizes the programmable nature of digital media. I don't want to belabor this point too much, but video games that simulate real-world physics are operating on procedures. Interactive storytelling games, right, are operating on lists of branching procedures as well. So computers operate, and everything on a computer that interfaces with the computer operates at a procedural level. The third is encyclopedic, which means that computers are incredibly capacious, perhaps the most capacious thing we've ever created. They store lots and lots of information on digital databases, allowing for the organization, access, and manipulation of large data sets. Unlike online encyclopedias like Wikipedia, online forums, for better or worse, digital libraries, search engines all operate with this in mind. And the fourth and final, and perhaps my favorite, because I love playing games, is the participatory nature of computers. So this affordance highlights how digital media enables users to engage actively with content, making choices and contributing to the experience in meaningful ways. Social media platforms, again, for better or worse, are participatory. Google Docs, perhaps much for better, is participatory. And what you're looking at here is actually a game that I created for ThoughtCon OX9 called ThoughtCon Plays Pokemon. How many of you have heard of Twitch Plays Pokemon, where you had a whole bunch of people on Twitch all inputting a bunch of different directions, and they were averaged together, and Ash Ketchum would like freaking out because you have hundreds of people telling him where to go at any one time or what to do. So this is a game where everybody at a conference, this hacker conference in Chicago, about 1,500 people were all pressing buttons on their badges at the same time, and Ash Ketchum was like, freaking out in real time. So why is this all important for hardware innovation? What I'm proposing we add to the conversation is that all of the components that we choose map to Murray's 4 affordances of computing. By mapping this language to hardware components, we can explore how these components want to be used and how to leverage them into our own technology in ways that are meaningful to a user. Furthermore, I propose 3 things. If we are going to analyze and design objects using basic components, servos, potentiometers, buttons, and so on, we need to understand what they are for. Number 2, if we're going to design objects using components, we need to know why we're choosing them. And number 3, if we're going to evaluate the things we create, we need some kind of a criteria, some kind of a language that we can use to evaluate them. And if this all sounds very academic, I promise it's not. I use this in all of the things I create. Hardware components in game consoles and controllers possess unique affordances that shape user interaction and engagement. By examining these components through the lens of affordances, both under Norman and Murray's frameworks, we can better understand how to design intuitive and immersive interactive systems of all kinds, including well outside the realm of games and into the realm of generalizable hardware. These concepts will also allow us to develop more creative solutions by having a deeper understanding of affordances, which can inspire unique uses of existing components and the creation of new ones. This could potentially, maybe, lead to interesting new designs in hardware. And I'd like to think that leveraging them has led to some interesting things already. All right, this is how we interact with pretty much every video game right now. There's a controller, there's a screen, and then there's some kind of a main station. Virtual reality works this way, computing games work this way, console games work this way. All of these have the same things. And I'm going to go through a real quick litany of what that means. You've got things like buttons, trigger buttons, directional inputs like a D-pad, analog sticks, touch inputs. You have no idea how long this list took to put together. Touchpads, motion inputs, gyroscopes, specialized inputs like microphones, cameras, IR sensors. You have other controls like start select, a home guide button, back buttons, volume controls. For outputs, you have display screens, LED indicators. You have other audio outputs like speakers, headphones, voice feedback, speakers and controllers. You have haptic feedback, motors in your controllers. You've got advanced haptics or precision haptic feedback systems, lighting effects, RGB LEDs, light bars. Okay, I'm going to stop. I have a whole list, and this is going to be in a post that I'm going to be releasing this weekend that breaks down all of these components and the affordances of them and how to look and map those to things that we make, okay? You get the idea. And it's important to note that all of these things can be endlessly configured in different ways. Microsoft has a couple adaptive controllers. This is a good one for people with certain disabilities and for everyone, for that matter, to use to interact with games in different ways. The game company Panic. How many of you have a Playdate? Okay, I do too. The game company Panic, they're a software company really, but they make games too, created a console called Playdate that uses many traditional features, right? A lot of that looks the same, but what's different? There's a crank for some reason. Why would they do that? It allows you to interact with games by turning it, or if you're my if you're my 7-year-old, by cranking it as fast as possible to the point where I'm worried he's going to break it off, right? Like, kids love that crank. Okay. Nintendo famously uses all sorts of interesting peripherals to interact with the sensors that they've got in their controllers. This is my favorite thing that they make on the right-hand side, the Nintendo Labo. If any of you have played it, I would highly I can't recommend it enough. And it's combination of cardboard and buttons and rubber bands that modify the controllers to create new controllers. You get to create your own things. But ultimately, all of these things use the same components to deliver these dynamic and varied experiences. So, by categorizing the affordances of the hardware components that we use in these devices and elsewhere, we can develop a comprehensive framework for designing interactive systems. This taxonomy includes directional control, analog sensitivity, action triggering, user feedback, and so on. All right, we're going to go through just a brief list of components, and then we're going to do another call and answer, okay? Because I'm not a person who loves talking all the time, even though it might seem like it. So, so just to give you an example of a few, these are joysticks, and this is a ChatGPT rendered image because I couldn't find an acceptable image of joysticks, so I apologize for that. Joysticks afford directional control and analog sensitivity, allowing users to engage with digital environments through precise and fluid movements. They serve as navigational guides, translating physical movements into virtual navigation. All right, let's take the novel part of this. I don't know if it's novel. Let's take the part of this talk that's the twist, though. If we take Janet Murray's 4 affordances, how would we apply them to something like a joystick? You have the procedural affordance. I would consider joysticks interactive pathways. They invite users to engage with complex procedures and algorithms, enabling dynamic control over characters and objects within the digital realm. Participatory. They're engagement handlers. They beckon users to actively participate in the game world, offering nuanced control and inviting them to become co-creators of their digital experience. Spatial. I think this might be obvious, but if it's not, they create a tangible connection to virtual space, guiding users through immersive environments with intuitive physical movements. And encyclopedic. They afford access to vast sets of motion data, translating physical movement into comprehensive sets of digital inputs. Is this all making sense? I hope it is. I'm not sure if this is okay. We're going to go through just a couple more, if that's okay. Yeah? Okay. Everybody knows what a D-pad is. It's just a bunch of buttons, but they're an elaboration on buttons. On the one hand, buttons afford action, triggering, and user feedback, providing clear and immediate responses to user inputs. They simplify complex interactions into discrete, easily understandable actions. As an elaboration of that, D-pads afford directional input and compact control, enabling precise navigation in structured environments. They facilitate menu interaction and offer a spatially organized method for input that buttons don't necessarily do. Okay, so again, procedural. D-pads afford procedural. They're directional controllers. D-pads afford precise control over directional input, enabling users to navigate menus and control movement in a structured manner. Participatory. They're choice facilitators. They invite users to make deliberate directional choices. Spatial. They're directional maps. They offer a spatially organized method, kind of like our operating system maps to understanding of the desktop space. The D-pad gives us an indicator of up, down, left, right. You can use that for the contra code and all sorts of other things if you want. And encyclopedic. They log directional commands, providing a comprehensive record of user interactions. I'm just going to do a couple more of these, and then we're going to get to the call and answer, I promise. Accelerometers. They afford motion detection and gesture control. The procedural part of them. They're motion translators. They translate physical movements into digital signals. Participatory. They're gesture interpreters. They invite users to participate through physical gestures. Does anybody remember the first time, when you got a Nintendo Wii and you realized that you could like wave things around and play golf and tennis and all that stuff? Does anybody remember that after that you learned that you could sit down and you didn't have to stand up and then you just like started doing that? Yeah, I remember that. Spatial, they afford awareness of spatial orientation, mapping physical tilt and motion. And encyclopedic, they collect and interpret motion data, providing a comprehensive record of physical interactions. I have done this for all, you remember that litany of components that I did before? I've done this for all of them. I'm just giving you an example, and I'm equipping you. I hope you're paying attention, because in our next call and answer, you're going to have to remember some of this, and I may even pair you off with some people for like a quick second to see if you can answer the questions on my test. Just kidding. I hope nobody has flashbacks all of a sudden to being, I'm not that kind of a teacher. Capacitive touch interfaces afford touch sensitivity and direct manipulation, facilitating smooth and responsive interaction with digital elements. What's the procedural affordance here? They afford the detection of touch input, enabling procedural responses to user interactions. Participatory, direct manipulation interfaces, they invite users to interact directly with the interface through touch. There's a sense of like immediacy and engagement with capacitive touch that doesn't quite happen with buttons, because you're actually like, your fingers are doing the thing And it's not just like mapping to a button or a D-pad. It's like your body's engaged with the actual game, right? Spatial. They provide a spatially organized surface for interaction. How many of you have like a Steam Deck controller? You know these things, and they've got the little pad in the middle where you can swipe your finger around. Cool. And for Encyclopedic, you have touch logs. They record touch interactions, creating a detailed log of user engagement and input patterns. Right after we closed our game company, I went to work for a company in Silicon Valley called MapR. It's a big data company that saved billions of points of data and would track like where your mouse is at every second on a screen. You can imagine that similar encyclopedic nature. You could store that data and understand how people are interacting with your game. You can make it more like a more dynamic experience, actually. And that's where a lot of games are headed with all this machine learning AI stuff. Anyway, finally, last but not least, potentiometers for analog adjustment and precision tuning, allowing for smooth control over parameters. They facilitate direct manipulation of system settings through a rotational interface. So the procedural, they're variable resistors, right? So they afford the adjustment of resistance, enabling fine-tuned controlling over procedural parameters. Participatory, they're analog adjusters. They invite users to make continuous adjustments, right? Enhancing engagement through smooth and precise control. Spatial, they're rotational controls. They provide a spatially organized method for control, offering manipulation through rotation, which is different than press, right? Rotation indicates like down and up in a way that a D-pad does not necessarily. And finally, encyclopedic, they're adjustment records. They log adjustments, creating a detailed record of user control parameter changes. Okay, here we go. So how do we leverage these affordances? What we need to do is define the desired user experience. How do you want people to feel when they interact with the thing that you've made? And then choose the hardware components that support that feeling. I hope when we're just going through all of the affordances here, you notice that those affordances create feelings within the people who are playing those games. So if you have a feeling that you want to evoke with the thing that you're making, whether it's a game or other generalizable hardware, you might want to ask, how do the components speak to that feeling? How do they, I know this sounds like hippy-dippy in a way, but it's true. They connect, right? They map to different feelings that we have about how we engage with things. Okay, so here's a question I'm going to ask 4 times. What components could have been added to the spatial, procedural, participatory, or encyclopedic nature of the game? And I'm going to present 4 games that I've made to give people additional feedback. Okay, so here's the first game that I made. This was 8 or 9 years ago. And what you'll notice, by the way, with each of these 4 games, I'm going to present them in chronological order. And because I'm making them for hacker events, I'm on a tight deadline, and so I don't have a lot of time to iterate. So what you'll actually notice throughout the years is that each new piece of hardware is effectively the next iteration because I've learned what doesn't work and what does work. This is one where almost nothing worked, okay? So I want to briefly take a look at some of these things, and this is the first one. This is Big Data Outbreak. This is for a conference of 500 people in Chicago. It was a big data conference, and it simulated a virus spread. This was before COVID. Using transceivers on the badges, communicating between themselves and Raspberry Pi kiosks. So the visual indicators on the kiosks showed the badges' statuses: green for clean, yellow for infected, and red for inactive. Inactive is not good. The project's core affordances reveal both challenges and successes. Unfortunately, and here's the big lose on this, and then I'm going to kick this back out to you. The complexity in the game was lost on most participants, which masked the procedural framework. Yet for those who understood, it spurred real-world, I'm going to call it avoidance behaviors, mimicking epidemiology. In other words, the people who knew that they were playing a game that was a pandemic actually avoided each other at a conference. They actively tried not to talk to each other. That part was intentional, but probably only 10 people out of a group of 500 actually knew that they were playing the game. The badges only had transceivers on them, and the kiosks were the only way to figure out what was happening. And oh, by the way, there was nothing to tell you which node and which circle there mapped to your badge. Super stupid and confusing, right? Okay, so here's what I'm going to do. Where's my question? Okay, so what components could have added to the spatial, procedural, participatory, or encyclopedic nature of the game to give people feedback. This is my call and answer. What could I have done differently? These are my failures, and I'm putting them out there for you. What could I have done differently here to change this? Right. So, something on a screen that would tell me how I'm participating in this game. Right. Absolutely. An LED on the back. These components can convey new kinds of information that the badge did not have. What I've got down here, yes, LEDs, the screens could have been different. You could have done haptic feedback when your static changed. Numbers on the badge, which is not really part of the 4 affordances, but even numbers that tell you what number you are and what corresponds to the nodes and so on. So thinking through these things and back on these things, by leveraging this idea of affordances and the 4 affordances of computing, I can kind of get a better idea of how to do this. Okay, so this is the second one I created, and I already talked a little bit about ThoughtCon Play Pokemon. So I'm going to talk about this one real quick, tell you what it is, and then I'm going to have you kind of like maybe talk with a couple folks near you for a minute, and then come back and tell me what you think is wrong with this one. Okay, so you can't really see it here, but the device had a screen up here, and then 3 buttons. And you got this badge, and then there was a screen located somewhere in the conference where Pokemon was happening. The problem was that people got the badge, and very few people had an idea that there was a screen at the conference that showed you what was happening when you pressed the buttons. So what were people doing when they were at conference talks? Just jamming on the buttons, like whatever, nobody's working together. Okay, that's my description of this. It was a little bit better than the last one. That's correct. That's correct. If they don't know what they're doing, they just start jamming on things. So what could I have done differently to help people learn from those mistakes faster? Provide instructions. Yeah, absolutely. I've got a screen. Could I not have used the screen to tell somebody that they were playing a game? Right? This is one of the affordances of the screen, is it can tell me that I'm participating in something. It can tell me what the procedures are to interact with the game, right? Okay. All right, here's the third one. So these are getting better. These are getting a little bit better. I by the way, did not, in this one, dictate the design. The people who were on the conference wanted stormtroopers, so we gave them their stormtrooper. Okay. So this is the ThoughtCon OXA badge. It has a speaker, a microphone. You can't really tell, but there are capacitive touch buttons down here and here. And then there's a capacitive touch slider. You know, like when you take 2 triangles and you can use it to detect when you're sliding. So it's got a slider on the side too. So speaker, it's got a microphone, it's got a Wi-Fi antenna now too. The prior one did as well, and all these other things on it. Okay, so the game experience for this one was a series of puzzles that people solved by pressing the capacitive touch things, and then LEDs, which were this is a backlit PCB. The LEDs would light up and tell you, and you're basically playing Simon, kind of, right? So you're playing Simon as you're doing this thing, and as you solve the Simon-like puzzles, you get new firmware. We wrote like this really interesting we wrote this interesting code that used IRC to push new firmware at the conference to all the badges, so the badges could they get over-the-air updates. So at the end of solving all of these puzzles, the microphone turned on, and we could hear the people who were holding the badge, the teams who were solving the puzzles, talking, and they were in IRC, and we would say, "We can hear you," and then they would go, "It's a cybersecurity conference." So what did they do? They immediately took the batteries out, and they did not play anymore, right? Okay, so a couple people got to the point where they solved all of these puzzles, but a lot of people, I think, were still confused because the capacitive touch pads, you can't really even see them here, were like masked. They were really hidden. Okay, what could I... Okay, so they were here, and then here's the slider. Okay, but if you're not looking for it, it's like, that's kind of hard to notice. So what could we have done differently? Think of mapping. What could we have done differently to communicate?
If there were like an etched A and B.
Yes. Yep. An etched A and B on the pads, because number one, it maps to our understanding of how controllers work, and it would call them out. So I'm going to show you my 4th badge, because this is a great tee-up. This is the 4th badge, where we learned a little bit, okay? So we took something that people recognized, and then we made an elaboration of it. So you've got a D-pad with 4 capacitive touch. You've got a select and start, both capacitive, and then an A and B, capacitive touch. You've got 2 rows of LED lights. You'll see behind each of these pads, you have backlit lights as well. And then there's a speaker on the right-hand side above A and B. Okay, so this is where we actually took the affordances and started thinking about components like big boys. Okay, you've got something that maps our understanding of how something should work. When you press one of the buttons, a light lights up behind the pad so you know you've pressed it. And a sound goes off on the badge too so that you know you've done something, okay? How incredibly satisfying as a person to be able to look at a thing and understand it and press something and for your expected outcome to happen. That's actually what good design is. Good design is when you do something and you get feedback that maps to your understanding of how a thing works, and we do that through affordances, right? Okay, so understanding the affordances of hardware components is essential for designing effective and engaging interactive systems. By synthesizing insights from design theory, phenomenology, media studies, I hope, I'm not sure if it did, this provided what I think are the beginnings of a framework for leveraging hardware affordances in game design and generalizable hardware. This is something I can't find any literature on right now. And so this is kind of new. And so as I said at the beginning of this talk, it's early work, and I'm looking forward to seeing if people use it and build on it for their own projects. In addition to the post that I'm going to be publishing on this, I'm going to be doing with a more detailed list of components mapped to these affordances. I have a few of my own projects that are leveraging this language, including the development of a new console right now that uses Meshtastic. Anybody familiar with Meshtastic? Are we all down with that yet? Operates on the 915 megahertz band, and it's a mesh network communication system, so I can communicate to somebody far away through other people who are running it. Oh, super cool, okay? So it's an interesting way to build localized games, and it's another new kind of component that makes me think about like what affordances bake into a localized communication game. Anyways, working on that right now, and then because I'm an academic and they make me do it, I'll be doing some research where I need to conduct interviews and develop a more comprehensive research framework. Do that. Real quick before I go to my last slide, that's my information down there if you want to contact me. I don't know why we call it X anymore, but it's Twitter or whatever. That's me on Twitter, and that's my information if you want to reach out. And more importantly, I'd like you to think about how you might incorporate the concepts of affordances, semiotics, and design into your own work to choose the appropriate hardware that speaks to the people who use your creations. Thank you. That's it.